Hello ladies and gentlemen, and welcome back to the 11th lecture for GGS300 Quantitative Methods for Spatial Science. Today we're going to have a fairly short run over some categorical difference tests, so it's not going to be too arduous for you. It maybe will only be about 20 minutes. And then this week there isn't going to be a laboratory, obviously, because we've got the midterm coming up, so you've got plenty of time to cover all of that material that we've just been through in the second third of what has been this semester-long course. Okay. Great, so those preparatory tests are now online for you. So basically these are the ungraded tests which prepare you for the midterm. And this is the second midterm, and it's going to be due again next Thursday. You need to have completed it by. I think if you prepare for the tests and then you take the tests and then you take the midterm, you should do very well on the actual test. So reach out to me if you've got any further questions, and I do wish you the best of luck, and I hope that you excel. Okay. Great. So today we're going to be covering these categorical difference tests. There's only a couple of them that we're actually going to cover. So obviously we've been focusing in the last couple of lectures on doing these inferential tests, so very much trying to formalize our hypotheses about the world and then actually test those hypotheses. So very much over here on the right hand side of this particular slide. So we're able to collect some data, we're able to then test hypotheses that we create, evaluate those hypotheses, and then actually either go back and define and develop the existing model or theory, or we can do, more importantly, the impact part. Okay, so we want to make the world a better place, we want to make people undertake better decisions, and one way to do that is by actually developing statistical tests to actually understand which path we should take forward. Okay, so which policy we should implement, or which strategy a business should deploy in order to go to market. So we've covered this flowchart previously, and within that flowchart we've been essentially focusing more on the kind of continuous stream of methods over here on the left hand side. So we've gone over so far differences mainly, and those differences have been between either a single group or two groups or more than two groups, and that's what we've been doing the last couple of lectures. In the future, we're going to be moving also onto this part where we look at relationships, so you can expect for us to cover correlations, Pearson's R, Spearman's rank, and regression analysis in the upcoming weeks. But today, just particularly to kind of close off this part, this middle section of the course, we're going to be going over what happens if you have discrete categorical data. Okay, so today we're going to be looking specifically at the chi-squared test, where you may have one sample, or contingency analysis if you've got two samples. So what we want to do is to actually look at the goodness of fit for the distribution of data that we get across nominal outcomes. Okay, so we're focusing very much on categories here. So, haven't we covered enough tests yet? So I do appreciate that we've covered a lot. I think maybe for the ANOVA part that we did, and also for this week, we've only covered maybe 2 or 3 each week. Arguably they're more complicated, but particularly when we're focusing on the two sample tests, we did end up covering a lot, because we ended up covering both parametric and non-parametric for independent samples and dependent samples. So we have ended up covering a lot. I'm not testing you in, the level of detail where you'll be assumed to be an expert in any one of these tests. This course is about introducing you to the breadth of statistical techniques and of giving you the ability so that you know which potential test to use in a particular case, and if you need to use it in the future you can. But if you're going to go off and you're going to do a PhD, then you might specialise in one particular type of test if that's particularly pertinent to the area that you're studying. So if you're interested in real estate analysis of prices, then you might be looking at time series data, which really we don't get much of a chance to kind of focus on here. If you're interested in understanding factors which affect the development of different regions, then you might be focusing more on kind of regression analysis and the correlation work that we're going to be doing later in this. or you could be going down more of a data science path, in which case you're going to be focusing more on the kind of funky new machine learning techniques, which kind of build off a lot of those more simple techniques that we covered this term, things like correlations, which you have to have that basis for probability and these basic understandings of tests before you kind of progress onto those more sophisticated techniques, which everyone loves right now because they're sexy. Okay, so let's get on to what we're going to be doing today, focusing on these nominal data aspects where we check the goodness of fit of different distributions of data that we might get, which is based on categories. So we're going to be focusing on the chi-squared goodness of fit, the Kolmogorov-Smirnov goodness of fit test, and then contingency analysis. So both the chi-squared goodness of fit test and contingency analysis use the chi-squared distribution. Okay, so we'll be working out how to cover that. We don't have a lab today, so I'll just be explaining briefly how you calculate this, and I'll provide you with a little bit of direction on the functions that you can use within R if you need to actually use some of these tests. And then I mentioned previously the Kolmogorov-Smirnov test, because I explained how we need to check that our data are normally distributed, and if you're kind of unsure about whether that is particularly the case, then one option that you might want to use to check that formally is by testing using something such as this test. Okay, so here we're going to be actually converting potentially continuous data into ordinal data in order to see if it fits a frequency distribution. It's a pretty common test, and I've used it before in my kind of early work when I was doing my master's, mainly just because when you're getting pushed through these kind of assessments that you might do, you want to demonstrate that you're using the right test, and always you kind of have that toss-up between is it a parametric or is it a non-parametric test, depending on whether you meet the assumptions or not, and this is kind of a formalized way for you to demonstrate that you know what you're doing. Okay. I think I mentioned before, in fact, earlier in the course, that if you do go on to do further research or anything like this, if you're being examined on your work potentially by an advisor or some sort of other external advisor, maybe for a PhD, then they can disagree with the conclusions which you reach. But the number one golden rule is that they must be confident that you followed the statistical tests that you're using correctly. Okay, so it doesn't matter if you reach different conclusions and they can pull you to parts over that, but they'll still pass you. But you have to make sure that the methods are sound and the methods are really good. So that's why you kind of really want to put a large emphasis on ensuring that you meet the assumptions for these particular methods. Okay, so what do we do within a goodness of fit test? Well, in this particular case, we are comparing an observed frequency distribution. So I'll give you an example of that when we move on in a second and we have some actual data. And we're comparing it to just the expected frequency distribution. Okay, so the type of frequency distribution that we would expect to occur randomly, just by chance. So how much does a distribution deviate from what is expected? And that's basically the fundamental way in which we then start to assess this observed data that we have versus the actual expected data that we have. Okay. So this deviation can be in a variety of ways. So it can either be based on whether the data are uniformly distributed, whether it's proportionally distributed or normally distributed. So there's a variety of different ways you can kind of approach this. You just need to make sure that you get the right statistics. So if you're focusing on uniformly or proportionally distributed data, then you need to make sure that you have the chi-squared test statistic compared to the normally distributed data where you need to focus on the Kolmogorov-Smirnov test. Okay. So we'll get to that in a little bit. We're going to start for now with the chi-squared goodness of fit test. So basically we need to actually compare the observed frequencies that we've actually obtained with some sort of expected frequency. So I'll give you an example of this shortly, but we just need to make sure that we actually meet those assumptions that we have for that statistical test to be valid. So we need to make sure that we have a randomly sampled single variable. We need to make sure that the variables that we have are nominal, ordinal, with frequency counts. So this could be downgraded data. If it's continuous, you need to convert it into either categories or ordered categories in order for you to use this test. And then there are some kind of frequency assumptions that we need to make sure that we're meeting. Okay, so we can't have any expected frequency of less than 2, and we can't have more than 20% of the expected frequency counts being below 5. Okay. So hypotheses. So for the null hypothesis here, what we'd be doing is we would be expecting that the population just fits the frequency distribution that we've got. Okay, so this is the kind of standard business as usual approach. And then that does contrast quite strongly with the alternative hypothesis, where essentially we would be expecting that there would be a significant difference of this frequency distribution versus the population. Okay. And chi-squared is the test statistic which we're going to use, and it's a very simple equation in order for us to get this. Okay, so we need to consider all of the categories that we have. So these are the nominal or ordinal categories that we are going to have within our data, which I'll show you shortly. And we need to sum across all of those for this very simple equation which we have here, which is basically just where we subtract the expected frequency count from the observed frequency count, square it as the numerator, and then divide it again by the expected frequency count. So this isn't challenging or arduous, or it shouldn't be at this stage. You know, some of the other equations that we've covered, particularly when we went over ANOVA, you know, having so many different stages and more complicated equations is a lot more challenging. So this should be fairly easy, which is why we haven't gone to the lengths of actually having a lab on this week, because hopefully if you can do the other work, this should be a piece of cake for you. So if all the observed values that we have are close to the expected, then the differences would be very small, the chi-squared test statistic would be very small, and therefore we would fail to reject the null hypothesis. Okay. If at least one of those observed values within those different groups is large, then that could lead to the chi-square being large, and then we would have probably much more substantial evidence to suggest that we should reject the null hypothesis. Okay. So there's this example in the book. Obviously, you need to make sure that you're reading the McGrew chapter each week to keep up with this content. So you need to be focusing on chapter 12 this week. But if you look at page 189 in McGrew, then we have a breakout box there, and it's going to be covering just this small little example related to the performance of schools. And whether schools are actually, the number of students at those schools which are actually performing above the national median on the SAT test, so the Scholastic Assessment Test or Standardized Assessment Test, whichever one you want to use as the acronym. But essentially we're just basically saying, okay, how many potential students after we've sampled are actually performing at this level above the national median score, okay? So we end up with these observed numbers of students across these 5 different schools that we've been out and sampled. So Muir, Pinchot, Carson, Hardin, Leopold, with 42, 45, 51, 47 and 60 students. Okay, so in this particular case, what we need to do in order to get the chi-squared test statistic is first we need to get the expected number of counts per group. Okay, so on the left hand side, this is how we do this. So to get the EI, we need to sum up all of the observed values. So we're just here. And then we need to divide it by K, the number of groups that we've got. So in this case, we've got 5 groups. Okay, that's the denominator. And then the numerator is just the sum of all of those samples that we've got from those 5 different groups. Okay, so if you sum up 42, 45, 51, 47 and 60, you get 245, which if we divide by 5, we get 49. Okay, so now it's very easy for us just to go into this equation and say, right, we know the number of groups, we've got 5, we know the EI, so that's 49. And then we just need to basically, for each one of the schools that we've got, insert the observed actual frequency count, okay? So here what we have is the insertion of that frequency count. So for Muir, 42, we're subtracting the expected frequency count 49 here from 42. And then we're doing that for each one of the schools. So we've got Pinchot here, we've got 51, this is Carson, 47, we've got Hardin, Leopold, 60. Okay, so obviously we're summing across all of these, and when we do that, what we end up with is a chi-squared value of 2.007. So it's not particularly large. And actually, we've got 4 degrees of freedom here. So remember, the degrees of freedom in this case is the number of groups that we've got minus 1. So we've got 4 degrees of freedom, and then we can find the p-value for this particular chi-squared test statistic, which is not a significant it's not a significant p-value. In fact, it's not a very strong effect at all. So in this case, we very much fail to reject the null hypothesis, okay? But I hope that by kind of showing you in this relatively simple way with this relatively simple amount of data, you're able to understand the actual math behind how we calculate this. And actually, I think what's really handy as well is if you want to understand this in greater detail, you can just tap it out in an Excel spreadsheet in order to understand exactly what's going on under the hood before you use it in the R code. And you know, I learned using SPSS, so this is kind of a proprietary statistical software before everyone kind of moved open source to using R. And actually, we didn't really learn how to do this in this way where you can kind of understand what's actually happening under the hood. And it's really important that you do know this. So I think that this is a much better way for you to kind of gain your long-term understanding of the subject by understanding both how to do this practically and also use the inbuilt functions that we have. So moving on now from the chi-squared onto the Kolmogorov-Smirnov test. In this particular case, what we're doing is we're using ordinal data in order to judge if that distribution fits some desired frequency distribution. So this can be any type of frequency distribution, but normally we're going to be testing for the normal distribution, okay? So does the data set that we've got, the data actually conform to that normal distribution shape? And we want to formally test if this is the particular case, because then it enables us to kind of point to it when we choose a parametric test and we can say, look, we didn't get a significant finding, which means that the data aren't different from the normal distribution, which means that we are justified in using a parametric test, okay? So the Kolmogorov-Smirnov goodness of fit test, we actually use cumulative relative frequencies in order to calculate this test. So it's arguably a little bit more complicated than some of the other ones that we've run previously. So what we're doing is we're comparing the sample data that we've got. So maybe we've got a distribution of data here, a histogram, and then we want to compare it to the perfect normal distribution. And the way that we do that is by converting from that ordinary perspective on the left-hand side here, where we just have the frequency, so the number of samples in each bucket, so it's up to 2,000 on the left-hand side here, versus on the right-hand side where we've got the cumulative histogram. So the y-axis actually is from 0 all the way up to the total number of samples that we have within our sample, okay? So to get the second bucket here, what we're doing is we're adding together the number of observations in the second bucket plus the first bucket, okay? And when you get to the third bucket, you're adding together the number of observations in the third bucket plus the second and the first, okay? So you're just going along each bucket and you're adding together all the previous values along with the new values you've got for that particular sample, okay? And that's how you get the cumulative distribution. Okay, so the logic here is that if the distribution is not significantly different, then we can use a parametric test. Okay, so we covered this before. Whereas if we get a significant result, then basically that's saying, well, actually, the data that you've got do not conform to the normal distribution expectation. That's because they're significantly differing from the distribution that we're comparing it to. Okay. How do we do this? So we've got a set number of requirements that we need to meet. Our objective obviously is to compare that random sample count that we've got for a single variable against some sort of expected count that we have, okay? So we need to have a single random sample, and we need to have continuously distributed data from the population, and we need to have ordinal data, okay? So even if it's continuous, like many times it will be when we're approaching this to see if it's worthy of using a parametric test, then we will be downgrading that data, okay? So the hypotheses that we have, obviously the null hypothesis is the kind of business as usual standard hypothesis, and that's basically where we would expect no difference between the observed and the expected distributions. And then the contrary to that obviously is the alternative hypothesis, so that's where the distribution that we get does not conform to that kind of expected distribution, okay? So it's significantly different. The difference here is that the test statistic is the D, and the D is basically the maximum difference that we get at any point between the observed and the expected cumulative frequencies. The way to get that is basically to subtract the cumulative frequencies for the expected values for the variable of interest from the cumulative frequencies for the observed value, and you find the maximum, okay? So it's not particularly arduous. However, it's actually kind of tricky to do some of the calculations to get to that point. So the Kolmogorov-Smirnov test, to do manually, you basically have to convert the rank data that you got to z-scores. You then need to calculate the cumulative normal frequencies and the cumulative relative frequencies, and then you need to compare those frequencies against each other with the normal distribution, okay? So we're looking for the maximum value. So if the difference is very small, then we have a large D. And if the difference is very large, we have a very large D, okay? And there's a table of D values that you're able to look up. But as it's kind of complex to run in R, it's like a little bit tricky. We are able to use the Shapiro-Wilk test to test the normality of data. So if you're doing this within R, then you can just use the standard Shapiro.test function, which if you need more help on and you want more information on, you can just do that standard R trick, which I showed you, which is just to do help, open brackets, put the name of the function in, and then run that, and it should just bring up the menu for the Shapiro-Wilk's test function that's available in R with all of the detailed documentation on the arguments and the use of the function, the interpretation of the function, for example. So the null hypothesis in this case is that the distribution is not different from normal. Okay, that's fine. That's consistent with the other things that we've looked at so far. And the alternative hypothesis is that the distribution is significantly different from normal. Okay. Although the Shapiro-Wilk's test does have some slight differences. Okay, so here we're looking for a W statistic, and it's slightly different from the other tests because a small W statistic indicates that you should reject the null hypothesis. So this is different from the other approaches that we've been taking. Okay, and then finally, the other issue I need to raise is just that the sample size can have a bit of a major effect here. So it can bias the results as the sample size increases. So as it's maybe more likely for you to find a significant finding, you need to take this into account. Okay, so you might want to change the probability value, the p-value that you use, recognizing that this effect takes place. So you might want to make it harder to actually see an effect. Okay. So just moving on to our final point here now for contingency analysis. So those other tests were specifically focusing on having just a single variable, whereas here what we're actually going to be doing is looking at whether we have two categorical variables, okay? So what we want to do is to test the cross frequencies of these two variables. So rather than actually comparing observed frequency distributions against a theoretical expected outcome, we're comparing the distributions of two actual samples that we collected. So maybe I send you out, you collect the data, you come back, and we have these two samples, and we want to compare the frequencies across these two sets of data. And the aim here is specifically to see if they are different or related, okay? So that's whether they are independent, so they're different, or whether they're dependent, so not related, so not independent, so that they are related. So the contingency analysis, it's a logical extension of the single variable goodness of fit. So this shouldn't be some sort of monumental leap in understanding for you. It just literally builds on what we've already been over in this very short video. We need to evaluate a contingency table, which we're going to run through in a second. And essentially this contingency table just contains a cross-tabulated frequency count across those two variables of interest for us, okay? So this basically helps to determine if there are significantly large enough differences between the expected and observed values. And then just one caveat here is that we've got to use absolute frequencies and not proportions for this particular case, okay? So, contingency analysis, this is called a variety of different things depending on which field you're in. So it can also be referred to as cross-tabulation, a confusion matrix, an error matrix. So when we're doing classification here, it can be called a variety of different things. I mean, I prefer just calling it a contingency table, a cross-tabulation table, because I think it's easier to understand. But essentially what we're doing is it's a matrix. So if you're not familiar with that, just imagine that we have two variables across the x and the y axis, and essentially we're putting all of the outcomes for each one of those variables across each one of across the cells. So we end up with a matching set of results. Actually, maybe it doesn't have to match, but the point is that you end up with all of the different outcomes that you could possibly have from those two different variables. Okay, so if we look at A here, A will be the count for the number of cases that had a 1 for variable x and a 1 for variable y. Whereas B here, this would be all of the cases which had a 0 for variable x and a 1 for variable y. Okay, so we should just be able to kind of fill this out so we get this cross tabulation. It's not hard, it's not particularly challenging, so hopefully you understand that, and there's more information in the book if you want to look at particular examples of where we may do this. So we're comparing these observed frequency counts for two different variables to assess independence. The requirements are that we have a single random sample, variables are nominal, ordinal with frequency counts, and then we also have those frequency requirements that we came across with the previous test. So we can't have frequencies less than 2, we can't have 20% of the data being less than 5, okay? So we need to make sure that we're meeting these particular requirements. The hypotheses, so for the null hypothesis, basically we're saying that the variables are statistically independent. That's the approach that we have, the business as usual case. And then the alternative hypothesis is basically where we expect that there's some sort of relationship between the variables. So the variables are not statistically independent. We're using the chi-squared test statistic here. And it's very similar to what we did before when we were looking at the chi-squared test. The difference here is that we also have the number of rows now introduced into our calculations. Okay, so we have the chi-squared test statistic down here. We need to sum up across the number of rows, the number of columns in the table as well. And then what we need to do is need to get the observed frequency count for the ith row and the jth column and subtract the actual expected frequency count for the ith row and the jth column, okay? And then we square them and then divide it again by the expected frequency count for the ith row and the jth column. This EIJ factor that we have here can be calculated relatively easily. It's just merely the sum of all observed frequency counts in the row multiplied by the sum of all observed frequency counts in the column, and then divided by the total number of observations, okay? So that should be fairly straightforward for you. It's not particularly arduous, and we've covered something similar like this already. We've just added another summation factor inside, okay? So let's pretend that we polled some GGS quant methods classes and we asked different majors how much do you like the quantitative courses? Okay, so always controversial, forcing people to do quantitative courses. I hope that this module, GGS300, hasn't been too hard for you, and that you know, even if it has been hard, hopefully you've got something out of it and you've enjoyed the content. You know, obviously I miss not being in the classroom with you and engaging with you. But you know, I think that hopefully you'll get something good out of it. So let's say we went off and we did this poll and we ended up with basically results as to whether people like quantitative courses. So either a lot, kind of marginally, or not at all. And we did that by major, okay, so whether it was the BA in geography, BS in geography, or other. And then basically we can get the column totals for each of these groups and the row totals, and these are all for the observed frequencies. So this is basically the data that we got through our sample. We can then get the expected frequencies here, so basically what we would expect by taking these rows and columns and then divvying those values out, and we end up with this 5.1, 5.7, 4.2 based on these different rows, for example. So once you've got that, it's fairly straightforward then just to calculate these statistics here. So you just need to subtract the expected value for the relative row and column here from the observed value, square it and divide it again by the expected value. And what you end up with is this set of numbers here. And then all we need to do is we need to sum these. So essentially what we get is when we run through this equation, this table is just covering this single part here, and then we need to sum by the rows and the columns. When we do that, we get the chi-squared test statistic of 2.7363, which is obviously pretty small. So that's giving you some indication already that we may not have a significant finding here. We need the number of degrees of freedom. So in this case, we have we need to take the number of groups that we've got and the number of rows, subtract 1 from each of them, we end up with 4 degrees of freedom. And then we can get a p-value based on that information, which here is 0.598, in which case this is far from being a significant result. So we fail to reject the null hypothesis, okay? You know, the results that we have may purely have just occurred by chance, so we don't seem to have any sort of strong evidence to suggest here at all that these are dependent samples or related in any way. Great, so that was contingency analysis very briefly, and this just kind of brings this whole section of the course to a close now, okay? So we've covered in the first third, we did introduction to statistics, kind of basic descriptive statistics, and we did a midterm exam there to cover that first third. This second third has been on using those inferential tests, focusing on the more kind of basic point inferential tests for a different number of samples, and then you know, covering parametric and non-parametric, and then now also kind of ordinal and categorical data. Obviously, we're going to have a midterm this week, which I wish you guys all the best of luck on. And then essentially what we're going to do when we finish this week is we have this final third of the course where we focus on these really exciting topics, and arguably much more exciting than the stuff we've just covered in the last couple of weeks, because we actually get onto correlation, regression, some more spatial statistics using more advanced methods like clustering, and actually I think that these are like much more fun methods basically. So I personally don't use that sampling kind of the sampling approaches that we covered in the last few weeks. Those inferential statistics, I don't use them very often. They serve their own purpose, but actually the types of things that I use a lot are regression and you know, the clustering methods that we're going to learn, correlation. These are some of the fundamental principles which underpin many of the kind of state-of-the-art quantitative methods. So I think that this will be an exciting part of the course and a good way to kind of round off the work that we've been doing. Great, well, it's been fantastic that you've been able to join me. Reach out to me if you've got any further questions. Good luck with the midterm. Make sure you take the tests and make sure you revise and really ace that. And I'll look forward to seeing you all again next week for the next lecture. Thank you. Goodbye.